Okay, so is this screen visible?
Yes, sir.
Okay.
Yes, sir.
Okay. So I think we can start this session. So good evening, everyone. I welcome you all to this week 3 live session on NPTEL course entitled Machine Learning and Deep Learning Fundamentals and Applications. So in this particular week, we will actually try to solve the quiz of week 1 and week 2. And at the same time, I have seen that the other TA actually he was actually solving the week 3 related problems. So likewise, in the next session, I mean by tomorrow's session, we'll see the questions related to week 3 as well. So in this particular week, I will be solving the week 1 quiz and week 2 quiz. At the same time, I have taken some related problems, which is basically have some relation with week 2 content. So it is basically how to find the decision boundaries and all. So we'll try to solve those problems. Okay. And another thing that I want to clarify is basically, if you have any query, you can post those queries in the Q&A section of the course website. And at the same time, we also have some constraints, like if you ask almost the similar type of question that is there live in the quiz, we will not be able to solve that particular question until the quiz basically, the due date is basically over. Then only we can solve those kind of questions, which is almost similar to the question that is there in the live quiz. So in the forum, I saw that several people have asked similar questions that is there, like we have true value of y, we have predicted value of y, then you have to find the bias and variance, which is exactly same as the question 5 of week 1, which was live at that time. So we'll not be able to solve those kind of questions because that is uh, beyond the guidelines of NPTEL. We have to refrain ourselves to solve the questions which are already there in the live quiz. Okay, so being said that, as because now I think week 1 and week 2 quiz have been evaluated, we'll be solving those 2 quizzes. And let me just ask you whether have you received any official solution from the NPTEL? Have you received any sort of solutions from the NPTEL? Sorry. I mean, did they provide any sort of uh, they have provided detailed solution? So they have provided detailed solution. Okay, so anyway, we can start solving the quiz. So let us start solving the week 1 quiz. So week 1 quiz is fairly simple. So in week 1, the first question basically states that in a binary classification problem, the confusion matrix size is of this sort. So as because the name suggests this is binary classification problem, so there are 2 classes. So let's say class true and class positive and class negative. So we'll have the confusion matrix like this. So this is for the positive class. This is for the negative class. Similarly, this is for the positive one. This is for the negative one. And at the same time, this side basically refers to the actual class, and this side basically refers to the predicted one. So this matrix is basically a 2 cross 2 confusion matrix. So therefore, the option D is basically the correct answer for this particular question. The second question states that what is the precision? So the formula of precision is basically the TP, that is true positive. So over here, the true positive basically your actual class is positive. You are predicting the class as positive again. So therefore, your prediction is true. And what is the type of the class? That is positive class. So therefore, this is called TP. Similarly, if I just go to this particular cell of this matrix, so you can see the actual class is negative and you are predicting it as negative as well. So your prediction is true. And what sort of class is this one? This is negative class. So therefore, this is TN, or the true negative one. So what about the off diagonal element? So in the off diagonal element, you can see that this is the actual class which is positive, but you are mispredicting it as negative. So therefore, your prediction is false and your prediction type is negative. So therefore, you can see this is called a false negative. At the same time, your for this particular cell, you can see that your actual class is negative and your prediction is positive. So this is where your prediction basically goes and your prediction is false again. So therefore, it is called false positive. So now precision is basically defined as TP divided by TP plus FP. So this basically refers the what is the proportion of the prediction of the positive entities. So this basically refers to the TP divided by TP plus FP. So how many you have positively uh, predicted, and at the same time, how many of the samples you have negatively predicted. That means you have done the false predictions, false positive predictions. So that basically, that ratio basically tells you that TP divided by TP plus FP basically gives you the precision. Okay. So in the next question, it states that in a binary classification problem, a classifier correctly predicts 90 instances as positive. So let us just read it once again. In a binary classification problem, so that means your confusion matrix size is 2 cross 2. The classifier correctly predicts 90 instances as positive. That means this is the true positive. Your original class is positive. You are correctly predicting it as positive again. So therefore, the true positive, basically, it is 90. Then it states that it incorrectly predicts 15 instances as positive when they are the negative. So can you tell me what case is this one out of these four?
False positive.
Sir, is it false negative?
False positive.
Yes, it is false positive. Let me tell you why. So see, they are stating that incorrectly predicts. So incorrectly prediction means this is false. It incorrectly predicts 15 instances as positive. That means your misprediction is on the side of positive class. So therefore, this is the false positive. When they are negative, that means actual class is negative. So over here, you can see the actual class is negative. You are predicting it as positive. So therefore, you can see the prediction is basically called false positive. So same as over here, incorrectly predicts 15 instances as positive. So the prediction is positive and the actual label is negative. So therefore, this is called false positive. So false positive is equals to 15. So FP is equals to 15. Then correctly predicts 90 instances as negative. So that means this is true negative. So this is 90. And incorrectly predicts 10 instances as negative. So over here also incorrectly predicts, that means your prediction is false. And what sort of prediction you are making? That is basically the negative. So that is why this is called false negative. Yeah, this false negative. So this false negative is basically 10. Fine. Now we have to calculate what is accuracy. So accuracy, basically it is referred as TP plus TN. That means how many you have out of all these samples, how many you have correctly predicted, be it a positive class or negative class, divided by total number of samples that you are basically considering for the prediction. So that is TP plus FN, FP plus TN. So therefore, if you just do this particular operation, so you will see 90 plus 10 plus 15 plus 90. So which is basically, if you solve this particular thing, you will get 87.8%. So the main concept is basically for this particular question, the main concept is to retrieve these values. So after reading this particular sentences, you have to retrieve that what entity these basically sentences basically refers to, whether this is true positive, whether this is false positive, true negative, or false negative. That you have to basically identify. This is the main crux of the problem. Apart from that, this is only a formula. You can remember that particular formula and then you can solve it. Fine. So the next question is F1 score. So based on the previous statements, you have to find out F1 score. So F1 score is basically 2 into precision into recall divided by precision plus recall. Now please tell me, what is the formula of recall? Yes, what is the
TP
formula?
by
Yeah, TP by.
TP divided by TP plus FN.
Yes. So do we have any sort of other nomenclature which is same as the formula is same as recall? Do we have any sort of other terminologies which is similar to recall? Anyone?
TPR and sensitivity.
Yes. So this is called sensitivity. So you'll see that in many of the questions, even like if you are writing the final exam as well, you can see you might see that similar sort of terminologies will be used interchangeably. So don't get intimidated with the terminology. So these sensitivity recall basically refers to the same quantity, TP divided by TP plus FN. Okay. So if I just solve this particular thing, so your TP is basically 90 and this is 90 plus 10. So what there it is, if I just, it is basically 0.9. Similarly, your TP is 90 and this is 90 plus your FP is 15. So this is 90 upon 115. So if you, sorry, 105. So if you just solve this particular thing, you'll get 0.857. Now, if you just plug in these values 2 into precision, so you got precision value 0.857 multiplied with 0.9 divided by 0.857 into, sorry, plus, what here you have plus 0.9, you will get 0.878. So if you just do it in the percentage form, it will be 87.8% again. So your F1 score is in percentage, it would be 87.8. This is in the whole number form and this is the percentage form. Okay, any query till this point?
No, thank you.
Okay, fine. Okay, so the next question. So this is the fifth question, I guess. Yeah. So the fifth question basically states that you have the actual values and you have some predicted values. So let us consider, if I just reframe the problem, let us consider you have y is equals to, you have, let's say, let's say you have a problem of linear regression. So till this point, you know what is basically linear regression means. Linear regression means you have to fit cards given some data points, or let's say you have to generate real numbers given some sort of arbitrary data points. So in the linear regression, let's say you have in the training data set, you have xi and yi. So these yi basically refers to the actual values of y, and these are the inputs. So this is the input, and this is actually the output. This should be expected output or the actual values, actual output values. Now, in linear regression, your main task is basically you have to fit line given these sort of points. Now, you basically try to learn some sort of a function like this, y is equals to ax plus b, where a is basically called the weights of the function, and this is basically the bias of the function that you basically try to learn using the linear regression method. Now, when you'll do the prediction, this y basically you can also annotate this particular thing as y hat, because you're trying to match, given some data points, you're trying to match the line that you are trying to basically estimate. The line equation that will not be exactly same as the original line of equation that you basically try to replicate. So therefore, you might incur some sort of loss. So therefore, this y hat is basically refers to the prediction values. So it would be something like this. So let's say your original data points are like this. Yeah. So your original data points, let's say it looks like this. And the original line, the original equation, let me just write some sort of linear curve then. So let's say yeah. So let's say your original data point basically looks like this. So let's say this is a non-linear curve actually, and you are doing the linear regression, and the linear regression output could be, let's say, something like this, which is almost equivalent to this particular line. So this has some sort of this original one, this green one is the original data trend, and this red one basically refers to the linear regression output. So that over here you can see that you are trying to basically approximate a non-linear curve through a line. So therefore there must be some sort of error. So that error over here, you can see that these are basically the error region. The hashed region basically refers to the error one. over here as well, this hashed area basically refers to the error region. So that means your prediction would be somewhat different than the original one. That is what is expected. So over here, the problem is you have been given some sort of y value. So the y values you can consider this blue, this green data, and this y prediction basically refers to this red line. So over here you can see that your original y is, let's say the first data point is 5, you are predicting it as 4. So therefore, it seems that you are doing some sort of uh, there is some sort of error in the prediction. So when you incur some sort of error in the prediction, given the true value is basically provided, so you have to calculate what is the bias of the model and what is the variance of the model. And mind it, this bias and variance of the model should be calculated based on the data that have been provided. So in the questions, you will see they have categorically stated that, for example, in this particular question, what is the variance of the model for the data given in the above question. So it is basically a data driven process. You might have seen the bias equations. So that is basically bias is basically expected value of the prediction minus the true estimate of the original actual data. So similarly, this particular function basically refers as bias is equals to, I can write it as expectation of y prediction minus y true. Given this particular data, this formula basically looks like this. You have some sort of predicted values, you have some sort of original values. So you just take difference between them. That is why that is how you'll get the error, and you just take the expectation, or in the more simpler format, I can write it as average of y pred minus y true. So if I just do this in a matrix format, it would be like you can take difference like this. Element wise difference you can take. So the element wise difference would be 4 minus 5, as because the prediction, the first element of the prediction is 4 and the first element of the y true is 5. So the prediction, the negation would be minus 1, then again minus 1, then minus 2, then 1, and then again minus 2. So please calculate the average value and tell me what is the value that you are getting to take the average. Yes, what is the average value?
-1.
Yes. So -1 is the correct answer for the bias. So this is the bias estimate. Similarly, what is the variance of the model? Now let me tell you the definition of variance again. Variance, let's say when you just deal about the basic, let's say basic Gaussian function. So basic Gaussian function tells you that, let's say your Gaussian function looks like this. So this is mu. Let me consider mu is a non-zero mu. So you have some finite mu, and all these points basically refers to the data points that is basically concerned from this particular distribution. So let's say this is x1, this is x2, this is x3. Likewise, you have n number of data points in the positive side. So let me consider, so it should not be, I should not say positive side, because I am considering mu is a non-negative mu. So this is not equals to 0. So on the right hand side, let's say you have n number of data points, and again in the left hand side, let's say you have n number of data points. So x of minus n. So this is, let's say, x of -1 like this. And this peak point is basically x naught. Okay. Now the definition of variance basically means that what is the dispersion of each of the data points from the mean of the data. So over here you can see, so this is the data point. Let's say x1 is a particular data point. So dispersion of all the data points from the mean. So by how you'll calculate the dispersion? So dispersion is basically the squared distance between the mean and the data point. So x1 minus mu square. Then you can take, then similarly you can take x2 minus mu square. So likewise, for all the data point, you have to calculate this dispersion. And then what you can do, then you can take the expectation of all these values and then you'll get the variance. So this is basically what is the definition of variance as far as the any sort of distribution is basically concerned. Similarly, you can see the basic formula of variance is this particular thing only, x minus mu ka whole squared expectation of this thing. So this is the meaning of this, the physical meaning of the equation. So from each of the point, you have to take the squared dispersion from the mean point. However, in this particular question, you can see you have to calculate the variance of the model. So variance of the model means here they are not expecting you to calculate the mean, because over here variance is basically meant like this, because you have some sort of original data. So this on the green line, let me again, if I just so this is the original, this is the actual, and this is what you have actually predicted from, let's say, the linear regression. So this is the LR output. So now at this particular case, for this particular problem, what they are referring by variance, they are referring that what is the dispersion from the original data. So this is the original data. And let's say at this point, this is your prediction. So what is the dispersion from this point to this point? So it is like y red minus y true. And then dispersion is basically calculated by the square distance from 2 points. Similarly, you can do this thing for all the data point. So therefore, you can take at the end an expectation. So in simpler form, I can write it as average of y prediction minus y true the whole square. So therefore, I can write it like this. So again, the main concept is basically you have the original data, you have some predicted data, you have to calculate the dispersion between the predicted data and the original data, and the dispersion is basically calculated by the squared distance, and then you can take the expectation or the average value. So by this logic, can you tell me what would be the answer? So before going to the answer directly, just similar to this, please calculate what would be the elements of this particular array. So likewise, we had calculated previously y pred minus y true. Similarly, please tell me what would be the elements of this particular array. Yes, anyone?
11414.
Yes. 1, 1, 4, 1, 4. And then if you take average, it would be 2.2. So therefore, this is the correct option. So the main crux of this particular problem is basically when you have been given two estimates. One is the actual estimate and one is the predicted estimate. So the equation of bias is basically what is the expectation. If I just formally or mathematically, if I just say, so this is basically expectation of the L1 norm and variance is basically expectation of the L2 norm. So this is what basically variance and expectation means when you have been given the actual estimates and the predicted estimates. Okay, fine. Any query?
Can you please repeat?
Okay, so from the bias one, right?
Yes.
Okay, fine.
Thank you.
So if I just again describe the problem, let's say you have been given some x and corresponding to that x you have particular y. So let's say xi and yi, this is your data set. So let's say your data set basically is referred as this has the data like the pairs are like 1, 1, then 2, 4, then 3, 9, 4, 16, and let's say 5, 25. So can you tell me what is the relation between x and y?
Square function.
Yeah, this is square function. So this is basically y is equals to x square, right? So if I just draw, so this is the true, these are basically the true estimates. So at 0, 0, let's say this is 0, 0. So then 1, 1. Then let's say this is 2, 4, 3, 9. So this should be a parabolic curve. So let us consider this is a parabolic curve. Anyway, the drawing is not pretty correct. This is the true relation between x and y. And that relation basically is y is equals to x square. Now, I have given you the data point. Let me just tell you that you have no knowledge about y equal to x square. I just have given you the data points. Let's say I have told you ki, do not just plot the data by yourself and try to create a relation. And I have told you to generate a relation between this x and y based on linear regression method. So in case of linear regression method, I just have now the problem that I have given is basically I have given you the data point and I have asked you to fit a line because fit a line using this data set which basically xi, yi. So you have to give me a line based on these data points. Now linear regression, in case of linear regression, you basically try to basically learn a equation of line such that you can fit this particular data. So that particular line is basically y hat is equals to m into x plus c. So this m in the notion of deep learning, machine learning, this is basically called the weight. And this c is basically called the bias term. So this bias is different from this bias. So you can also think it as intercept. as far as lines equation is being concerned. So this is the slope of the equation and this is the intercept of the equation. So over here, as because you've been given the data which is a non-linear trend. So you can see this equation is a non-linear equation. So this data has non-linear trend, non-linear, but you are trying to fit a equation of line using these data, as because your equation, governing equation is y equal to mx plus c. So anyway, what you will do is basically, let's say you have drawn a line like this. So this is the linear regression output. So when you do linear regression output, given this x, you have predicted, the predicted output is this one. At this particular point, let's say this is at x equals to 0. This is at x equals to 1. So you have predicted this over here, predicted this over here. So that means if I do it with some other color, which is contrastive. So at this particular point, you can see that you are obviously you are making some sort of error. You are trying to approximate a nonlinear equation using a lines equation. So obviously there should be an error, and these error can be seen from here. So this is the original curve. If I just join the black dots with the original function, that is y equal to x square, and you are basically trying to approximate this nonlinear curve using the linear function. So therefore, you can see that you are making some sort of error over here. So at x equal to 1, red one is your prediction. This is your y pred. And this black one is basically your y true. So this is the situation. So from here also you can see your original data is 5. Original output should be 5. You are predicting it as 4. So that means again over here also you are making some sort of misprediction, which is obviously it should be there because you are approximating a nonlinear function with a linear one. Now, given these condition, so let us consider now your problem is basically you have a linear regression model. You are feeding xi, you are getting yi hat, or let me call it as y prediction. And at the same time, you have the true outputs as well. If you do not have true output, how basically you will be able to understand that your model has performed well or not? It is same as like the confusion matrix, creation of confusion matrix kind of thing. Confusion matrix is for the classification problem, and over here this is a regression problem. Now you have this y true and you have this y predicted. So now over here you have to see that what sort of error you have made. So to calculate the error that you have perceived using this linear regression method by approximating a nonlinear equation through linear equation, there are two measures. One is called bias estimate and another is called the variance estimate. So bias estimate is basically average of, just you take the distance between these 2 points. That means y prediction minus y true. So simply it basically means that y prediction से y true कितना differ कर रहा है. If it is differing very high, so that means your model prediction is very bad. If the difference is basically very small, that means your model prediction is very good. So bias estimate is basically simple negation of y pred to y true. That means true value से predictions कितना differ कर रहा है. Similarly, variance का मतलब है, so this is also called as expectation of L1 norm. And in case of variance, the equation just changes slightly. So this is basically squared difference. So this is y pred minus y true plus square. So you take the squared distance And then you can take average across all the data points. So this is basically the meaning of variance estimate. And after you do this, you can plug in all the values and you can get the result. So this is basically when you've been given the two estimates. One is the actual estimate. So this is the actual one, and this is the predicted one. So you have two different conditions to measure the performance of the model. One is the bias and one is the variance. So variance is basically bias is basically expectation of the L1 norm between y pred and y true, and this is variance is expectation of L2 norm of y pred and y true. You just plug in the values, you'll get the answer. Okay. Any further queries on this particular thing? Okay, if you have,
Before,
yes.
in the last, there is a variance के लिए सर आप कुछ स्क्वायर में ले रहे थे. Actually,
We have done square.
डिस्टर्बेंस हो रही है. Sorry to tell you again कि ये variance का जो है ना आपने इसमें स्क्वायर नहीं. हाँ ठीक है सर. It is okay, fine. I got it.
Yeah, we have taken square. Acha, this one let me remove.
Yes.
Actually,
Thank you.
okay. Okay, so this is the next question. Basically has some connection with the previous question. So the same concept that I have just illustrated. So you have been given the X points. So over here you have the data set like this. You have pair of X and Y. This is the X value and this is the corresponding Y value. And you are doing some sort of linear regression. So in linear regression, you basically try to find Y hat, which is basically Wx plus B, weights and biases. You basically try to learn the learnable parameters are basically W and B. These are called the learnable parameters. So the question is find the parameters of the linear regression model. So we can see that the linear regression model basically tries to find what is the value of W and what is the value of B. So this is the training data set. So given this data set, you have to tell me that what would be the value of W and what would be the value of B. So how did anyone approach this particular question in the quiz? And how did you solve?
First, we will find out the bias.
Okay, how?
Subtraction from the predicted value to true value. Component
Okay,
bias.
So this bias in the previous case, this bias is something else from this particular bias. So over here, this bias basically means the model performance. This has relation with the model's performance. And this bias basically tells you about you have a line, let's say you have a line. So this is what is basically meant by bias B, or this is also called the intercept of the equation, intercept of the equation of the line. And this W basically refers to the slope. So this is the slope. So this we call it as weights. So this is same as y is equals to mx plus c. So you have to find what is the value of m and what is the value of c. Yeah. So how did you proceed with this? Okay, so let me give you some hint. So over here, let's say you have y is equals to wx plus b, and you have certain number of data points, right? So I can take the mean estimate. So if I have to take mean estimate, so it would be expectation of y and expectation both the sides. I'm taking expectation wx plus b, and I can again rewrite it as expectation of w into x plus expectation of b and expectation of y. So I can rewrite it as expectation of y is equals to uh, w into expectation of x, as because w is a single constant value. So the w will come out from the expectation component, and the second. Yeah, and this E of B, it is basically B only, as because expectation of the constant will be same as the constant value. So now over here, expectation of y hat basically means summation of yi w into again 1 upon n summation of xi plus b. So this is your equation number 1. So please uh, do this particular operation and tell me what are the values. So you are just basically taking expectation of this y vector and expectation of this x vector. So what is the expectation of x?
3.1.
2.5.
Yeah, 2.5 actually. So yeah, so this is 2.5 w plus b, and I have the value already. So it is 8.58851. So this is your equation number 1. This is your equation number 1. So now you can see that you have two different two variables that you have to basically get the values of. So for solving this particular equation, it is not able to will not be able to solve this because you have two variables and one equation. So we have to generate an auxiliary equation. So how we can generate an auxiliary equation? We have to find some other means. So one very basic mean would be, this is, let's say, equation number a into x on both sides. So it would be x into y, w into x square, and then b. And then what you can do, you can take expectation, so x y, and then you can take w, and I can write it as directly this. An expectation of b is basically means that b only. So this is my second equation. So over here, expectation of xy basically means that you multiply x and where is the cursor, and y, and then you can take expectation. So it is basically 1 upon n summation xi yi, then w into 1 upon n And then you have this particular equation. Or if I just expand this, it would be, you can write it as expectation of x and expectation of x. So it would be 1 upon n xi, 1 upon n xi. So you can write it like this as well. So over here, so what you can see is basically summation xi yi, then w by n summation xi square, and then over here it would be, so if I just so it would be n into b. So this is 2a. So if you just do all the summation and multiplication and then you take the average, it would be 380.2522, and then it would be w multiplied with 145, and then over here it would be 25b. So if you solve this particular thing, you will get this final answer, final form. And now you can see you have two equations. So this let me write it as 2c. Now you can see that you have two equations, two different equations, and the variables are w and b. So you can solve this, solve 1 and 2, and then you can get the final results. And if I just let me and if I just have to write it over here, the answers are W and B are 2.0065 and 3.5722. So you can use any sort of online calculators to solve this particular equation. So there are two equations, you can solve these two equations and we'll get the value. So the main crux of the problem is uh, you have two different variables, and this is the equation of the linear regression model. It basically tries to learn a line of equation. So therefore, you have to solve the value of W and the value of B. So how you can do this? So you have to think about some mathematical manipulation. So one manipulation is basically, which is very simple. You just take the expectation on both the side and we'll get the equation number 1. Now you can see the problem is you have two different variables, and the equation is, you have single equation which is not solvable. So therefore you need to create an auxiliary equation. And how you can create an auxiliary equation? Over here I have multiplied with x. Similarly, you can do the same with multiplication with y as well. And then you can solve the particular equation. You will get something like this solvable format. And then from equation 1 and equation 2, if you just solve this, you will get the weights and biases of this particular equation. So this is the correct answer. Okay, fine. So finally, if I just have to write the, let's say, final form of the linear regression function that you have learned over here. So your LR model, after doing training on this, all this data, so the LR model is basically y hat is equals to 2.0065 into x plus 3.572. So now you can see from these data points, you are getting a line of equation like this. Now again, the point is, these are the actual values. So these are the actual values, and you are trying to fit a line which basically fits all the data points. But frankly speaking, you will not be able to fit all the data points because of the nonlinear nature of the data. Or let's say in the first class, you have seen that you have some sort of data distribution plus noise. So over here, you can see that these are this decimal point expansion. These are basically called the noise components. So you will try to approximate the equation of line and you will try to fit as much as possible, but you'll not be able to fit completely well, like in the previous case. So you'll try to fit all the points, but due to inherent property of this line, you'll not be able to fit all the points correctly. So there should be some sort of mismatch. So that mismatch, basically, if you feed now, you feed all these data points, let's say -2 if you feed, then you'll get y hat 1 when x is equals to 2. Similarly, you will get y hat 2 when x is equals to -1. So likewise, if you feed all this data, you will see you are making some sort of error, which is not exactly same as the original one. So that means you will do some sort of mispredictions. So the next question is trailing of that question. So the trail basically says that find the MSE of the above equation. Now, how will you find the MSE? Can you just tell me from this particular logic that I have provided? You have the original estimates.
Sir, variance is that you have calculated that predicted minus true and square, then you have taken the average. So that means square error. That is the same thing.
Yes, that is same. Yeah. So that is the crux of the problem. So MSE is basically you have to calculate y pred minus y true का square sum and then 1 upon n. So this is basically the average process. So how will you get y pred? Your x is, if I just copy this thing, -210 minus 2 1 -1 0 1 2. अच्छा 1 से लेके 7 तक है. So 1 2 3 4 5 6 7 and you have some values of y and your linear regression equation is 2.0065x plus 3.5722. Now please tell me how will you find the y pred? Just the first component, if you just if you can tell me what would be the first element of this y pred vector. Yes, please calculate this one.
Sir, I am getting the first value is minus 0.4408.
Fine. Okay, 1 second. Let me open my calculator as well. So 2.0065 multiplied with -2 plus 3.5722. Yes, minus
0.4408.
yes, minus 0.4408. So likewise, what you have to do is basically, if I just copy this particular thing as well, I think will not be able to copy this. So by any way, you can see the your original first element was minus 0.5267, and over here your prediction is minus 0.4408. So this is the point that you are trying to fit the equation, but you will not be able to fit exactly same as the original one. There should be some error. So the original one was 0.51. 5267. 5267. So similarly, you can calculate all the values for all other cases. So let's say what you have to just basically do, you put -1 over here, plug in the value of x, and then you will get the value of y hat. So simultaneously, you can do for all these cases, and you have the actual values corresponding to all these x values. So you have two vectors. One is y pred and you have y true. You have to take the negative, then you have to take square, and then you can take the expectation. So you'll get a single value. So I hope you can do this, right? Because unnecessary, I have to do the computation.
Yes, we can do
The idea is, I think, you're able to understand the idea.
Yes, sir. We can do
Okay.
this.
Yes, yes. Okay, so the next question states that a model with high variance and low bias means, so let me just, so over here, x-axis basically, let's say model complexity, and y-axis, let's say basically it refers to the measure of model performance. It could be any sort of thing like L1 loss, L2 loss, or any general error. So that is why I'm not explicitly writing. Someone is trying to join, but okay, so I'm not explicitly writing the type of loss. That is why I'm annotating it as measure of model performance. It could be anything like L1, L2, any sort of error. So let's say at the time of training, so this is the training error. So this is training error card. And let's say this is the testing error card. So I have so first thing I have to tell you that what are the different sections of this graph basically means. So let me just uh, segment or segregate the areas of the graph. So let's say I should have it like this. So this is the very low complexity part, low complexity model, low complex model. This is, let's say, mid complex, and this is highly complex. So in these cases, in all these cases, you can see, so this is the testing error, this is the training error. So bias basically means what? Bias basically means that the bias basically means that how you have certain model predictions, you have certain actual values, and you have certain model predictions, how close they are. So if they are very close, so that means you have high bias. So for example, over here you can see that your training error, or let's say your training error is like this, and testing error is also kind of similar, like their range is kind of similar. So that means their training errors are similar, that means their estimate could be kind of similar as well. So this is what is called high bias region. However, over here you can see that your training error is very low. That means at the time of training, you are doing very good classification or regression. But at the time of testing, you're not able to do, you're not able to predict it correctly, or you're not able to predict the values for the regression part. So over here, you can see there is a huge gap between the training error and testing error. So that means the variance means what? Variance means from a particular point, what is the dispersion? So that is basically a minus b ka whole square and then you can take expectation and all. So I'm not going into that. So the dispersion over here, you can see the dispersion from one point to another point is very high. So that means I can say this is high in variance. And we know that there is a trade-off between variance and bias. So the trade-off is something like that. If you have high bias region at this particular area, so the variance is low. So how you can see the variance is low? So you can see that the dispersion is quite less because the type of error or the range of error in the training case and testing case is almost similar. So therefore the dispersion is very less, and that is why the variance is also very less. And similarly over here you can see that dispersion is very high, so there is a high variance, and as associated with that, due to the bias variance trade-off, the bias is low. So now we have to see, and you need to see that what is the complexity of the model associated with that area. So over here you can see that we had very low complex model. So at very low complex model, you can see that the model capacity is very small. However, at the time of very high complex model, so that means it is something like that. If you have some data point like this, and let's say Professor MKB has also shown some graphs like this. Let's say in the linear regression model, your number of M, or let's say number of W, is 9. So therefore you'll see something arbitrary like this. It will try to fit all the data points. So let's say the data points are like this. So when you take number of coefficients in the linear regression model is, let's say, 9. So for example, in the previous question, we had only one coefficient, that is W. In the W vector, we have only one coefficient. Instead of that, let us consider we have taken 9 coefficients. So then your model response would be something like this, something like very arbitrary. It will try to fit all the data points. So that means at the time of training, the error would be very less. But at the time of testing, it will not be able to perform well because it has it has not understand anything from the data. Rather, it has memorized all the data. So that is what happens in case of any machine learning and deep learning problem. After you go certain epochs, you will see something like this. So this is also called in the deep learning part, you will see this is also called overfitting. Overfitting means at this point of time, जो भी model है आपका, that will start memorizing everything. Or in layman term, it would be like the model सब कुछ रट्टा मार लेगा. It will try to memorize everything. So as it has memorized everything at the time of training, it will give very low error. Now when the unseen data will come, as because it has not learned anything, इसने सब कुछ रट्टा मार लिया है. So therefore your model will not be able to perform on the unseen data. It is same as like you are doing some sort of, like there is a kid, you are teaching him or her mathematics. So in the exercise book of the mathematics, you have solved each and every problem, and the kid basically solves that particular problem every day. So what will happen? By the basic inclination of human memory, the kid will try to memorize the mathematical problems very well, what he has seen in the exercise book. Now in the exam date, if I just tweak some problems, which is not same as the questions that he has seen in the book, he will not be able to answer those questions generally. And what is the reason? Because he or she has memorized everything, सब कुछ रट्टा मार लिया है. So that is why at the time of working out the problem in what are there in the exercise book, as he or she has learned everything or memorized everything, the error will be significantly low. But at the time of exam date, as because the questions are totally different that he or she has seen in the book, so you'll see the testing error or the performance would be pretty bad. So you can see the loss is pretty huge. So the performance is very bad. So as far as the linear regression is basically concerned, so this is what happens when you take very high complexity model. So high complexity, you can also make an analogy like if you solve that particular book every day, so that could be a high complexity thing. Rather, a single book, if you are solving that particular book every day, so that you can consider as a high complexity model. Rather, a low complexity model would be something like this. A low complexity model would be you have two different textbooks. You are solving those two textbooks as well as you have some other sources from where you can get some new questions, and you are solving those questions as well. So that means you are not relying on a single book. You are having different sort of sources and you are inferring the mathematical problems from different sort of sources. Then what will happen? Your intuitive thinking will be go up. Intuitive thinking will go up, and therefore you'll be able to understand the things that how to solve different sort of questions. So this is what basically meant as mid complexity model. So over there, you are not relying on a single book and you are not solving that particular question every day. So therefore, high complexity is diminished. So you are basically focusing on understanding the things rather than memorizing the things. So if you see the mid complexity model, so the mid complexity model may not fit each and every point, but it will give some very less amount of error. And the error, as because the error is not that significant, it will be able to understand the thing. So over here you can see the data, the line is basically able to understand the trend of the data. So you can see this follows the trend of the data, rather it just fits the data. So this particular problem is called memorization, and this particular thing, this red curve, this basically means the understanding the trend of the data. And the understanding of the trend of the data will be only happening only in the case of mid complex model. So over here, the highly complex model refers to the high in variance and low in the bias. So over here, you can see that a model with high variance and low bias means it can be too simple to understand. So this is false, because too simple to understand basically refers to the low bias condition. Yeah, so an excellent performance in the training data, but a significant decrease in performance while evaluating on the test data. So you can see that the performance very much degrades over here, as because you can see the loss is going up. So that means performance is degraded. So significant decrease in performance while evaluating on the test data. So therefore, this particular option is the correct one. So the next question is, which of the following techniques is used to prevent overfitting in the machine learning? So this is what we have already talked about, what overfitting means. So overfitting means at the time of training, you will get very uh, significantly less error, and in the testing set, you will get significantly high error. So this is what is called overfitting. Now, how to reduce overfitting? So to reduce overfitting is basically, you can see, to create complex machine learning models. So complex machine learning model basically is susceptible to overfitting. So therefore option 1 is incorrect. Train the model for more epochs. This could be an answer. This could be an answer, but provided there should be a condition that you increase the training data. Let's say you have 100 number of samples and you are training the model on 100 number of samples multiple epochs. So as because they have wrote like more epochs. So if you are running a particular model which is on 100 number of samples, what will happen over the time of epochs? It will start memorizing the things, which is again will cause the problem of overfitting. So therefore, this is also the incorrect one. Had it been the case, like train the model for more epochs with larger amount of training data, let's say instead of training with 100 data, you're training with 1 million data. So there, the model will try to learn from the data rather than memorizing from the data. So in this particular case, because they have not mentioned this thing, increase the training data. So training on more epochs would not give you a good result. Second is to increase the variance of the model. So over here, you can see the variance is increased at this particular area. So the increase in variance automatically means that increase in overfitting. So anyway, this option is incorrect because variance and overfitting, they are linked. If you increase the variance of the model, the the chances of overfitting will also shoot up. So therefore, this last option is also incorrect. So to avoid the condition of overfitting, we basically use regularization techniques. And what sort of regularization technique we can use? You have seen in case of the regression, linear regression lecture. So there are L2 regularization, L1 regularization, and there are several sort of weight normalizing regularization techniques are also there. But L1 and L2 regularization you have seen already in the classes. So this regularization technique basically tries to prevent the value of W to shoot up to a very high value. It restricts the value of W so that the overfitting can be diminished. Okay. So this is where we end with the week 1 quiz. So now we can go to the week 2 quiz as well. So in the week 2 quiz, the first question is basically on consider a binary classification problem with two classes A and B and the prior probabilities that have been given. So P of A. So class A's prior probability is 0.6 and class B is 0.4. And you have the feature X. And feature can take two values. So I can put close brackets over here. So it can take two values, either 0 or 1. So can you tell me that what is the distribution of the feature? As because it can take binary data, either 0 or 1. What kind of distribution this X could have? Yes. What could be the distribution of X? It can take two values, either 0 or 1. That means either success or failure. What could be the possible distribution? Okay, so this can take Bernoulli distribution. That's because you have seen the Bernoulli distribution probability mass function. Bernoulli distribution is a discrete distribution. So instead of probability density function, it will have probability mass function. So the mass function is basically defined as if let's say x is small x, if the random variable is taking small x value, it could be either 0 or 1. It would be p of x 1 minus p of 1 minus x, something like that. Either if it is falling into the class A, so the p would be 0.6, and x basically can take either 0 or 1. So by that logic, uh, you can understand what basically Bernoulli's distribution is. Okay, so keep in mind, I have talked about Bernoulli's distribution in the later slides or in some of the later questions. There is something related to this one is also there. So let us now move to the question again. So x belongs to 0 and 1. Fine. So they have also given some of the class conditional probabilities as well. That is p x1 given A is equals to 0.8. Px given px0 given B is 0.7. So can anyone tell me that x can take either 0 or 1, as because we already have told you that this has a similar property as Bernoulli's distribution, as because this can take discrete outputs. So what could be px of 0 given A, and what could be px of 1 given B? What would be the values? Yes, anyone? You have been given px1 given A. So what would be the value of px0 given A? Yeah, am I audible? Hello.
X not X not
Point two.
0.2
Yeah,
and
it would be
0.3.
0.2. So this would be 0.2. And the logic is basically very simple, because you can see x can take either 0 or 1. And let's say the class dependency of the belongingness is A. So it belongs to class A. So total probability would be 1. So if I just have to find that x naught of A, so it would be 1 minus px1 of A. Similarly, over here, x1 of B would be 1 minus. So yeah, so this would be 0.3. Fine. Now we have to find that determine which class the classifier will classify when x belongs to. So the question is, when x equals to 1, we have to identify that x belongs to what class. That means we have to find the posterior probability at that time for both the classes, and for whichever class the posterior probability is high. So that means the particular x equal to 1 sample belongs to that particular class. So let's say p of a x equals to 1, we have to find out. So what would be the formula? Please tell me what is happening. Yeah, what would be the formula for this one?
That will be likelihood into prior divided by evidence that we could do.
Apply. So what would be the formula?
For finding that x is equal to 1 belongs to A.
So what would be the formula? Let's say P of A given X. This is the posterior probability. This is called the class conditional probability.
Likelihood that you have to multiply, that is 0.8 into probability of A, that 0.6 divided by that evidence we have to calculate.
Yes, yes. Yeah, you're correct. So it would be P of A multiplied with P of X equal to 1 given A divided by the total probability. So total probability, you can calculate it as P of X equal to, 1 given A plus, it can also fall into the class B as well. So it would be P of B, P of X equal to 1 when it belongs to class equal to B. So this we have to calculate. So if I just plug in the values, it would be 0.8 divided by, multiplied with 0.6, and over here as well, 0.8, 0.6 plus your 0.4 multiplied with 0.3. So 0.48 divided by 0.6. So which is 0.8. Similarly, we have to find probability of X equal to 1 when it basically belongs to class B. So that means posterior probability of B given X equals to 1. So the formula would slightly change and it would be in the form of P of B, P of X equals 1 given B divided by this whole term. This would be same. So the denominator is 0.6, and over here we are doing multiplication between 0.4 into 0.3 divided by 0.6. So it would be 0.2. So now you can see from these two computations that P of A given X equals to 1 is greater than P of B given X equals to 1. So from this, what would be the inference? X belongs to which class?
Class A.
Yeah, X belongs to class A. Because we have to see where the posterior probability is maximized. If the posterior probability is maximized, so we can say that the corresponding data belongs to that particular class. So over here for class A, the posterior probability is high, so X belongs to class A. Now, Bayes decision theory assumes that, yes.
Can you please show the last screen? Yes. Thank you. Thank you.
Okay. Okay, so the next question states that Bayes decision theory assumes that the feature vectors are dependent on each other. The feature vectors are normally distributed, feature vectors are identically distributed, and feature vectors are uniformly distributed. Okay, so have anyone answered this particular question in the big quiz? You can raise your hands. Have you solved this particular question? You have Bayesian decision theory, and you have different 4 conditions regarding the feature vector. They could be dependent on each other, normally distributed, uniformly distributed, and identically distributed.
Identically distributed.
Yeah. So what is the reason?
मेरा क्वेश्चन गलत हो गया था ये तो
Sorry.
यार I had marked wrongly in the assignment.
Okay, you have marked
I
wrongly.
remember this is the answer. Yes, please explain.
Okay. Any other person who has answered this particular question? I just want to know that if you have answered this question, that then what was the rationale behind it? Anyway, I will be answering this question. Okay, I hope nobody has answered this question. Okay, fine. So we will analyze all four options and we'll see that what should be the best possible answer for this particular question. So in the previous question, that is why I was saying that just keep in mind that the data in question number 1, the feature, so X is the feature and X could take only two cases, either 0 or 1. So that means it can take discrete values or discrete levels. And discrete level basically corresponds to the distribution of Bernoulli's distribution. So you can see in this particular question, feature is distributed in Bernoulli's distribution. So P Bernoulli. So you can see, and in the weekly lectures, when you have done the discriminant equation, discrimination function, that is, you have solved those g of x's for different classes. The equation was g of x is equals to p of omega given x. What type of distribution did you considered over there? Just tell me. So you have solved discrimination function using Bayesian theory. Already you have solved these discrimination functions. We had a lecture. We had, I think, 2 to 3 lectures on that. And g of x is basically p of omega given x. Then you had a distribution function. What distribution you have considered there? Yes, anyone? Yeah, can you recall multivariate Gaussian distribution or multivariate normal distribution? Which was something like this. Yes. So Vaibhav has raised his hand. So you can recall this particular equation. So this is the equation of In case you do not know what is the distribution of the data, so for understanding the distribution, what are the techniques that you use? You have learned this thing in week 3. Please give me the answer. If you do not know the distribution from the data, then you try to learn the distribution from the data itself. So what are the techniques that you use? Yes, anyone? Please tell me what is the content of week 3? What is the content of week 3? What is the main gist of week 3? Anyone? Okay, so in week 3, basically the lectures are on 2 topics. Broadly, we can classify the topics in 2 parts. One is basically where you know the distribution, but you do not know the parameters of this distribution. For example, you do not know the parameter of the mu vector and the sigma vector, sigma matrix. This is a covariance matrix. So to identify the value or to identify the elements of the mu and sigma, you have different techniques like parametric technique, non-parametric technique. One of the very popular technique is basically MLE estimation, maximum likelihood estimation, where you basically try to maximize the probability for that particular variable. So that is basically MLE. So this MLE basically applicable where you know the distribution, but you do not know the parameters. And the second part of the lecture is on where you do not know the distribution itself. You try to estimate the distribution. To estimate the distribution, you basically use Parson window. You use KNN based methods. Okay, fine. So the main analogy that I was trying to draw over here is basically feature can take Bernoulli distribution, Gaussian distribution. It can also take uniform distribution or any arbitrary distribution. So therefore, the main point is the the Bayesian theory do not explicitly give you certain condition that your feature should only take either uniform or Gaussian or normal or Bernoulli. It can take any sort of distribution. So categorically stating that feature vectors are uniformly distributed, this is not true, because it could be feature vectors. If it was written may, then you could have answered, you could have ticked this particular question. As because the features can take any sort of arbitrary distribution, either it can take Bernoulli, it can take Gaussian, it can take normal distribution, it can take any sort of distribution. So finitely saying that feature vectors are uniformly distributed, that is incorrect. Similarly, feature vectors are normally distributed. In the class lecture, you had seen that you have solved the math, theoretical part using Gaussian distribution. So you could have thought that, okay, in the class I have seen that features are normally distributed or Gaussianly distributed. But in the question, in this particular question, you can see that your feature is Bernoulli distributed. So that means again, you cannot finitely state that your data or the feature will only follow the normal distribution. So by that logic, again, normal distribution is also nullified, as because your data can take any arbitrary distribution. Okay, we have nullified 2 features. Last one is feature vectors are dependent on each other. Again, you have solved three different cases. One is you had only the diagonal elements. This was independent. You had another covariance matrix which was filled with all the entries were filled. All the entries were filled. So over here only you had sigma 1 square, sigma 2 square, sigma 3 square, like that. All other elements were 0. So this is called independent case. In the last week session also I told you that what is the meaning of independence. So when the off diagonal elements are 0, that means these features are independent on each other. And over here, if you have non-zero off diagonal elements, so then you can see that features are dependent on each other. And if you recall, while doing the Bayesian discrimination theory, so over there you have solved for this case also, this case also. That means for independent case also, dependent case also. So that means your feature can either be independent or it can dependent as well. It can be dependent as well. So therefore, again, categorically stating that features are dependent on each other, this is also false. Now, you can see that features are identically distributed. What is the meaning of identically distributed? That means you have feature, let's say x1, x2, x3, dot, 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 let's say xn, or let's say xt. So that means you have d-dimensional features. So in case of d-dimensional features, the distribution would be a multivariate distribution. And when you had solved that multivariate distribution or multivariate Gaussian distribution, you thought that all the data were following the multivariate Gaussian distribution. That is why the equation was same for all the cases. That means all the data you consider, all the data are coming from IID. This term also you have heard in this particular week session. So this is called independent identical distribution. So over here, the distribution is identical. So that means all the features are basically coming from the same distribution. But the distribution could be anything. It could be Gaussian distribution, it could be Bernoulli's distribution, it could be uniform distribution, it could be anything. But the main point is the equation of the distribution would be same for all the data points. So that means the data is identically distributed. So that is why this particular answer is the correct one. So the next question is, assume the word offered occurs in 80% of the spam messages in my account. So from this particular line, what could be the mathematical expression that you can basically infer through? Assume that the word offered occurs in 80% of the spam messages. What sort of probability is this one? Yes, anyone? Probability of something is 80%, I mean 0.8. So what is the condition? So this states that this is the word offered occurs in 80% of the spam messages. So I can write it as the word offer given spam message. So offer given spam is equals to 0.8. So this is basically the inference of this particular line. Let's assume offer occurs 10% in my desired emails. So that means P offer on non-spam is equals to 0.1. If 30% of the received emails are as this would be spam. are spam. So what is the meaning? Please tell me what is the meaning of this particular line? Probability of what?
Probability of the spam.
Yeah, so probability of the spam class is equals to 0.3. So now you can understand that if your probability of spam is 0.3, so probability of non-spam would be 0.7. Total number of message probability, total number of email probability is equal to 1. If you are getting spam probability is 0.3. So all other will be non-spam. So that is why 1 minus 0.3 is equal to 0.7. Fine. And the question, the last line basically states, and I will receive a new message which contains offer. What is the probability that is spam? So now tell me what it basically means. What would be the argument of this particular probability function? What they are referring to?
The offer is given, we have to find out the probability of spam over offer.
Yeah. So it would be probability of spam given offer. So we have to find probability of spam given offer. What would be the equation again? Would be probability of spam class, then probability of offer given spam. This is the, again, this is class conditional probability. This is prior probability. And this is posterior probability. And divided by the total probability. So it would be spam, probability offer, spam plus probability of non-spam, offer, non-spam. So what would be the answer? In the numerator, it is 0.8 multiplied with 0.3. Denominator 0.8, 0.3. And then non-spam is 0.7. And offer non-spam is 0.1. So if you solve this, the result would be 0.774. So I hope there is no query because it's a simple one. Okay. So the next question is the optimal Bayesian decision process or decision theory given these conditions: minimize error rate, maximize error rate, maximize loss, minimize loss. So what would be the answer? Have you answered this question? Please raise your hands if you have answered this question. Yeah, the question is the optimal decision in Bayes decision theory is one that minimizes, maximizes all either loss or error rate. What would be the answer?
Minimizes the loss.
Okay, and what is the reason for that?
For the correct decision, the loss should be minimum. I think based on that.
Yeah, this is partly true, but uh, in many of the cases in the Q&A section, I saw that Bayesian decision theory, people basically they are referring to Bayesian minimum error classifier. So in our week's lecture, we have learned two different classifiers. One is Bayesian minimum risk classifier. Another is minimum error classifier. And in this particular question, they have not explicitly mentioned that which Bayesian decision theory they are referring to. They have just written Bayesian decision theory. They have not specifically mentioned whether this is minimum error rate classifier or minimum risk classifier. Rather, the striking thing in the question is they have written the optimal decision theory. This particular word is very important, optimal. So we have to understand out of these two classifiers, which one is the optimal one. So in case of Bayesian minimum risk classifier, I don't know whether you can recall it or not. So risk of, let's say, alpha 1 given x is basically lambda 1 p of omega 1 given x lambda 1 to p of omega 2 given x. So this is what if x belongs to omega 1 for Bayesian minimum risk classifier, where the risk should be minimized. Now for a two-class problem, if we consider lambda ij is equals to 0 and 1, and 0 when I is equals to j, and 1 when I is not equals to j. So you can say that alpha 1 given x for this particular condition for a two-class problem, it would be, if I take 1 is basically 0, so it would be for lambda 1 2 it would be 1 multiplied with p of omega 2 given x. Now you can see if x belongs to omega 1, according to Bayesian risk classifier BRC, our alpha 1 given x should be as minimum as possible because risk should be minimized. And if I do the same, x belongs to omega 1 for Bayesian minimum error rate classifier, there the error should be minimum. So if we choose to x belong to omega 1, the error is basically p of omega 2 given x. This should be minimized. So you can see if I pose certain conditions like this, like lambda ij is equals to 0 and 1 for two different cases, you can see the final equation of risk minimizes to this one, and where the risk should be minimized. This is as far as Bayesian minimum risk classifier is concerned. And Bayesian minimum error classifier says that the error should be minimized. That means P of omega 2 given x should be minimized. So you can see that in this particular equation, this should be minimized. So as if this has to be minimized, this particular term has also to be minimized. So you can see for this particular condition, the Bayesian minimum risk classifier is equivalent to Bayesian minimum error classifier. So this proof is also given in the week lecture, in week 1's lecture, when the Bayesian minimum risk classifier converges to Bayesian minimum error classifier. So we can see that Bayesian minimum risk classifier is more generalized classifier. This is more generalized classifier because from Bayesian minimum risk, I can go to Bayesian minimum error. but the reverse is not true. From minimum error, I cannot come back to minimum risk classifier, because in case of minimum error, we do not have any sort of loss function there or penalty function there. So this Bayesian minimum risk classifier is more generalized, or this is called the optimal Bayesian theory. So by optimal decision theory of Bayes decision theory, they basically try to mean this Bayesian minimum risk classifier, and Bayesian minimum risk classifier minimizes loss or risk. So that is why your answer is loss. It minimizes the loss function, not minimizes the error rate. This is true for this case, Bayesian minimum error classifier. As because they are talking about the optimal one, so optimal one basically means the minimum risk classifier, which reduces the loss or risk. So that is why your answer should be minimize the loss function. This is the reason. Had it been the question like what is the case for Bayesian minimum error classifier, your answer would be this one. But as because this is optimal one, they are referring to risk classifier, so the answer is this one. Okay. And this particular term is called penalty or loss due to uncertainty of classification. So this lambda ij is basically called penalty or loss due to uncertainty of classification. So therefore, what are the components in this risk term? So in the risk term, you have this a posteriori probability or the posteriori probability, and as well as this lambda term, which basically means the penalty due to uncertainty. So the next question basically asks you to evaluate that what risk function of Bayesian decision theory combines. So the risk function lambda alpha 1 x is basically lambda 1 p of omega 1 given x plus lambda 1 2 p of omega 2 given x. So this term is uncertainty, and this term is basically the posterior probability or likelihood. So let us see. So this basically states that so uncertainty or penalty or loss. Okay. So it basically combines. You can see this is loss function. So this loss function basically refers to this uncertainty or penalty or loss, and the decision rule. Now, what is the decision rule that you can infer to? So this decision rule is basically the posterior probability or the likelihood. And this posterior or likelihood basically comprises the conditional probability and the prior probability. So this risk component comprises penalty or loss or uncertainty or the posterior probability or likelihood, which is also called the decision rule. And this decision rule also comprises conditional probability and the prior probability. So therefore, this one is the correct answer. And the training set and testing set, any sort of decision theory that is basically made up on training set and testing set. Training set is used to train the classifier, and test set is basically used to test the classifier. This has no relation with the it has no relation with the combination of risk function. So therefore, it is incorrect. Prior probability and the likelihood function. So likelihood function you can see over here. Likelihood function depends on prior. So therefore, explicitly saying that it depends on prior probabilities as well as likelihood, this is incorrect, because likelihood comprises prior, but the reverse is not true. At the same time, the decision boundaries and the feature vectors. Again, decision boundaries and feature vectors is subject to constraint that, let's say, this is your two classes. This is P of omega 1 given X, and this is P of omega 2 given X. So the decision boundary is already associated with the classifier, and feature vectors are already associated with the classifier, but this is not associated with the risk function. So therefore, this also is not the correct one. Okay. Then you have the loss function used in risk-based decision theory, quantifies the cost of different types of error is equal to likelihood function. So likelihood function basically means that P of omega given X. Risk is not equal to P of omega given X. When your uh, problem is binary classification problem and you impose certain conditions, this condition, then you can say your risk is basically equals to posterior probability. Other than that, you cannot say. So this is not true. Then loss function ignores the prior probabilities. Again, the loss function basically comprises, you can see that the loss function associated with the posterior probability. Posterior probability equation P of omega given X is, if I just, the denominator is P of X, it is P of omega into P of X given omega. So you can see posterior P of omega given X is proportional to P of omega. So that means there is some relation. So you cannot say that it ignores the prior probabilities. So therefore, this is also incorrect. Third one is not used in decision making process. So in risk classifier, you can see that risk equation already associates this loss function or the penalty function. So it is also false that it has no role in decision making. Obviously, it has role in decision making because you are multiplying this with the posterior probability. So therefore, this is also incorrect because you can see that risk is proportional to the loss function. So therefore, they have relation. So you cannot say that it is not used in decision making. Indeed, it is used in decision making. So therefore, you can see that the first one is the correct answer. Okay. So the next question is the risk-based Bayesian decision rule accounts the consequences of different decision by considering the number of features in the dataset, complexity of the classifier, uncertainty in the data and associated losses, mean and standard deviation of the feature vectors. Fine. Again, you just recall the equation of risk, it will give you the answer. So over here, 1 P of omega 1 given X plus lambda 1 to P of omega 2 given X. So you can see this is the uncertainty component. So over here, you can see this uncertainty component in the data and associated losses. So therefore, this is the uncertainty component of the data, and this is also the associated loss or the loss function. So majority of the cases like this kind of uh, intuition based questions or statement based questions, just refer to the classified equation and that particular and just skim through that equation. You will get to the answer very easily because majority of the question will be based on this particular equation only. So we have seen that the consecutive 4 questions were basically uh, made on this particular equation only just by changing the nomenclature. So you have to be aware with the nomenclature of this particular thing. This is called uncertainty. This is called loss function. This is posterior probability. Posterior probability indeed comprises the prior probability as well as the class conditional probability. So all these things, nomenclatures, you have to be aware with. Okay. And last question is the generalized Bayesian network that represents and solves the decision problems under certain knowledge is known as. So please tell me, this is a theoretical question. What would be the answer? Yes, anyone? What is the answer for this particular question? You had seen these type of diagrams like this, let's say F, A, B. So B is dependent on F and dependent on A. So what are these graphs called? What these diagrams called? This is called the influence diagram. This is influence diagram. Okay. So has anyone solved this particular question? You have this Bayesian network and you have the following conditions. So from this particular Bayesian network, the initial one, you have been given probability of flu is equal to 1, probability of cough given flu. Probability of cough given flu is 0.8. Then probability of cough without flu. This is basically the bar of F. That means no flu. So probability of cough without flu is 0.3. So probability of flu, if probability of flu is equal to 1, 0.1, then probability of no flu or without flu, it would be 1 minus P of F, that is 1 minus 0.1, that is 0.9. Now we have to find what is P of F given C. How to find this? P of F given C, what would be the equation? Yes, anyone? This is simple base theory. Bayesian rule you have to apply. What would be the equation?
P of fever.
P of
F.
F then it would be P of C given F,
F.
then P of F, P of C given F. So this is for the flu part. Similarly, you have to incorporate the non-flu part as well. So that means without flu one. So that would be P of F bar, P of C given F bar. So if I just plug in the values, it would be 0.1 multiplied with 0.8 divided by 0.1, 0.8. Then you have 0.9 and 0.3. So if you solve this, it would be 0.2286, which is 0.23. Okay, so this is the last question. But before that, let's say you have two cases. Please tell me, what is the conditional probability in these two cases? What do we mean by conditional probability first? From this particular diagram, let us start from this particular diagram. What do we mean by conditional probability over here? How do you define conditional probability here? So let me tell you a few things, like for this particular course, if you are actually willing to write the final exam, so please brush up the concepts of basic probability, just +2 level probabilities. Don't go deep into that, but like these Venn diagrams, and from these Venn diagrams, how to conclude the conclude to the probability equations. These things you have to be aware with. Just brush up those things. I know that you all know this, but with time, uh, सब चीज निकल जाता है. So just brush up these things once. Mainly the intuitive part is required. So P A given B basically means the proportion of event A and B when they occur simultaneously divided by the probability of B. So that is what A by probability of A given B means. So you can see that A given B means जब A और B दोनों एक साथ हो रहा है, what is the joint probability of that, or what is the proportion of that joint probability divided by the probability of B. That means given probability of B. So if I just go from this point to this point, so given the probability of B, what is the proportion of event A and B which basically occurs jointly? So now please tell me that in this particular diagram, which part basically refers to this particular statement where A and B occur simultaneously or jointly?
Intersection part.
Yeah, this intersection part. So over here I can write P of A intersection B divided by P of B. P of A given B. So this is the fundamental formula for conditional probability. If you go to any +2 level book, +2 level mathematics book, you will see when they define conditional probability, they first define this. After that, due to certain conditions, you come to the conclusion of Bayes rule. There the numerator part basically changes. But the fundamental formula for A given B or the conditional probability is this one. Depending on different condition, you will see different formula come upon. Now tell me whether A and B, they are dependent on each other. They are dependent or independent. What sort of case is this one? Are these two dependent events or independent events? What sort of event these two are? When you see any sort of intersection, you can refer to those cases. Let's say you are extracting two different features from the data. So the main point is that when you see these kind of probability things, you can also draw analogy as far as the machine learning topics are also being concerned. So you can see that these are two distributions and features are also have certain distributions. So you can take some analogies like in this way. This will help you to grow intuitive knowledge. So over here you can see that these two features have some sort of overlap nature in them. So this is called dependent case. That means they are overlapped on each other. They have certain dependency. And in the last lecture, we talked about independence. Independence means these two have no correlation with each other. यहाँ पे correlation है, दोनों के बीच में similar type of nature है, इसीलिए दोनों के साथ mix हो जा रहा है. So that means basically they have certain correlation, and correlation अगर है, so that means those cases are dependent cases. So therefore, over here, A and B are dependent events. Now, tell me that whether A and B are dependent or independent in this particular case?
Independent.
Yeah, so it would be independent. So over here, the equation would be, and for independent case, what would be the, if you just expand this particular thing, A intersection B, what would be the expression? If A and B are independent on each other, they have no correlation, what would be the next step?
Union.
Sorry?
Union will take.
So for independent case, PA intersection B, as because they have no dependency, they have no common part in each. So therefore you can say that PA multiplied with PB. So the probability for the independent case multiplies with each other, right? So over here, PA dot PB. Therefore I can write PA given B, if I just PA given B is equals to PA dot PB. So therefore, PA given B is equals to PA. So this is what happens when A and B are independent on each. And this is what happens when A and B are dependent. And this basically gives you the Bayes rule. In case of Bayes rule, then you basically change this particular thing. Fine. Now, why I am talking about all these things? Because they have asked for the above question, for this particular question, where we have basically extracted P of F given C. We have extracted P of F given C. Now they are asking that are C and F, these two independent? If C and F are independent, then from this particular equation, we just have seen if A and B are independent, then A given B, I can write it as P of A. So by the same logic, if F and C are independent, I can write it should be equal to P of F, isn't it? Any query on till this point? If P given C, if C and F are independent, I can write this, right?
Sir,
Yes.
one query is that why you cannot write down P? It is probability of C given F.
Probability of C given F. Because see, in the last question, we have been asked P of F given C. So we have to
Okay.
trail
Okay.
this particular question.
Okay.
Okay. Okay. So this was the condition that we had derived. If A and B are independent on each other, I can write P of A given B equal to P of A. So by the same logic, I should be able to write P of F given C is equals to P of F if C and F are independent. Now let's see what are the values. P of F given C, P of F given C in the last question, we have evaluated the value is 0.23. And what is the value of P of F? The value of P of F is given as 0.1. So that is 0.1. So we can see that these two are not equal. So therefore I can write P of F given C is not equal to P of F. So that means if I am not able to write they are equal, so that means they are not independent. So the answer is they are not independent. So this is how you have to evaluate. So if the two probabilities to two events are basically independent on each other, I would have written this particular thing. But from the values, I can see P of F given C and P of F, they are not equal. So therefore, they are not independent on each other. Any confusion?
No.
Okay. So, so this is the last question for week 2 as well. So we have covered week 1 quiz as well as week 2 quiz, and I will be sharing the slides as well in the Google Sheet link. I think you know that how to go to that part. So let me just show you once again. So if you open the course website, you can go to the problem solving part. Then you can go to the problem solving recording. Then you can click here. And this will take you to a Google Sheet. So over there in this particular folder, so this particular section is of mine, and the later part is for Anirban. So we have provided the presentation link folder as well. If you just click on this particular folder, this will take you to the slides. So from there, you can get the annotated slides, which will have the solutions. And as well as I will upload the videos as well. So anyway, you will get the videos through from my YouTube channel as well. So if you have any further queries, you can ask me. Otherwise, we can stop this session here.
Thank you so much, sir, for giving the detailed discussion about the assignments. So just want to know कि जब हमें ये पूरा कोर्स करना है तो जैसे अभी आपने बताया प्रोबेबिलिटी का हमें ब्रश अप करना है और भी कुछ
थोड़ा
ऐसा
सा प्रोबेबिलिटी ब्रश अप कर लीजिएगा.
हाँ और भी कुछ ऐसा मैथमेटिक्स है या जो मतलब जिसकी बिल्कुल रिक्वायरमेंट है
अच्छा
अच्छे
हाँ
से
तो
समझने के लिए
machine learning deep learning course के लिए there are two things that you have to brush up. One is
Yes.
basically the linear algebra लीनियर अलजेब्रा में भी, लीनियर अलजेब्रा इज अ वेरी वास्ट टॉपिक। उसमें भी आप सिर्फ सिस्टम ऑफ लीनियर इक्वेशंस कैसे सॉल्व करना होता है, मेनली वी सी इन द कोर्स की हम लोग बड़ा बड़ा जो भी इक्वेशन होता है विल नॉट सॉल्व दोस थिंग्स एनीवे, वी विल राइट कंप्यूटर एल्गोरिथम्स, they will solve it for you. But the main point is, let's say you are reading linear independence of the vectors or any vector space. You can uh, try to visualize the theory part. For example, in many of the cases you will see there are mathematical notations. Just try to understand intuitively that what basically that mathematical notation signifies in real life. So that is what you have to understand. So that is fine. Only linear algebra part and the probability part. And probability part, I am referring as because anyway in the final examination you have to write, you have to solve some numerical questions. So over there, probability might because linear equation you will be able to solve anywhere. कभी थोड़ा लेंदी प्रोसेस हो जाएगा, कभी थोड़ा मतलब अगर आपको ट्रिक्स याद है यू विल बी एबल टू सॉल्व इट क्विकली. But probability is something that you have to somehow you have to brush it up so that you can recall the formulas as well. Probability or linear algebra, these two things you have to look back.
थैंक यू सर फॉर गाइडिंग अस. अगर आपके पास कुछ इसके लिए मतलब कहीं से कुछ हेल्पिंग अलजेब्रा जैसे आपने बताया बहुत वास्ट है, तो कुछ कुछ भी
जैसे
मटेरियल, स्टडी
कि
मटेरियल अगर हो तो
जैसे
प्लीज
कि
शेयर कीजिए.
हिल्बर्टस्टाइन, you can see in YouTube. If I just let me just go to YouTube. So there are 35 videos. I will not refer to like watch all the videos, but you can see some of the videos. This particular lecture series is, in my opinion, this is the best lecture series on linear algebra. So this particular lecture is why I'm referring to this particular lecture series, because he will give you some intuition as well. In many cases, you will see that people just solve the equations or people just solve the notations or matrices. Instead of that, he will give you some intuitions as well. For example, if you do a into x equal to lambda into x, for example, for the eigenvector decomposition or eigenvector or eigenvalue extraction. So the main point should be, as far as machine learning is concerned, uh, eigenvalue eigenvector computer can efficiently extract well rather than humans. We will take time, computer will take very small amount of time. But the main point is we should know the intuition behind this particular, why I am doing a into x, and why if I equate a into x into lambda into x, why I am getting eigenvectors. So this particular questions that why I am using this particular formula. So this particular lecture series will help you to understand those intuitive concepts. So you can see some of the lectures till eigenvector would be fine. That much is required only.
थैंक यू सर, थैंक यू सो मच.
Okay, so I think now we can end this session. So let me stop recording.